Section 4.2, Part 1 of the notes for exponential functions. In this part, we're going to talk about exponential functions, properties of exponents, and look at some graphs. First of all, I want a quick reminder of properties of exponents. So you can read through these and write down these examples if you feel like you don't have these memorized. An additional property that we'll need to know and use a lot in this concept is if we have a to the m over n, so that's a fraction in the exponent, we can rewrite it as the nth root of a to the mth power. We could also choose to write it as the nth root of a to the mth power. So either way works. Sometimes it's easier to write it the first way and evaluate, while other times it's easier to start with the second way and evaluate it that way. From this definition, we should know that a to the 1/2 is equal to the square root of a to the 1/3 is equal to the cube root of a, and so on and so forth. So this is kind of a fact that I'm going to assume that you know throughout these notes. If you don't know this, then make sure that it's written clearly in your notes. We're going to start out with example 1, where we're just going to be evaluating some exponential functions. So we have f of x equals 2 to the x, and we want to find f of -1. So all we're going to do is plug -1 in for x and evaluate it. You can evaluate it one of two ways. You can plug it in your calculator, or if you notice that it's a negative exponent, that means that my base of 2 is going to move to the denominator, so I get 1 over 2. Example 1, part B, same thing. We're going to evaluate f of 3. So we plug 3 into our x value. We get 2 to the 3rd, which equals 8. Example C, we have f of 5/2. So we're going to plug that in for x in our equation. The way that we're going to simplify this is we are going to rewrite 2 to the 5/2 as 2 to the 5th to the 1/2 power. The reason I can do that is because 5 times 1/2 is equal to 5/2, excuse me. These are equal, and my operation here is multiply. So I'm kind of like unmultiplying the 5 and the 1/2. Next, I'm going to evaluate 2 to the 5th, and I get 32, still to the 1/2 power. 1/2 we know is a square root, so I have the square root of 32. I can rewrite 32 as 16 times 2. The square root of 16 gives me 4, and 2 stays in the square root. You can always check your answer on this problem by plugging 2 to the 5/2 into your calculator. Example 1, part D. Now we're going to evaluate f of 4.92. So this one we're definitely going to need a calculator for. We cannot do this one by hand. And we're going to approximate. Make sure that you read My Math Lab and see if it wants you to round to 1, 2, 3, 4 decimal places. Make sure you make note of that. So we define exponential functions as if a is greater than 0 and a is not 1, then f of x equals a to the x power defines the exponential function with base a. So remember, the a spot in this equation is our base, and x is our exponent. Here we have the graph of an exponential growth function. From left to right, we're increasing, so we call this a growth function. We're not going to focus too much on graphing in this concept, but there will be times where you'll have to pick which graph goes with a function. So this is for the function f of x equals 2 to the x. Our domain is all real numbers because those arrows span all the way to the left and all the way to the right. Our range is from 0 to infinity. The lowest that my graph goes on the y-axis is 0, and then it moves up towards infinity. If I plug in -2 through 3 into my equation, I get out these y values, and I can plot them to make my graph. So notice that growth functions are increasing on the entire domain. Also, the x-axis is our horizontal asymptote. And our graph is going to always go through the points -1, 1 over a, 0, 1, and 1a. Next, we have an exponential decay function, so it's decreasing on the entire domain. Domain and range are the same. The x-axis is still our horizontal asymptote. We still go through the same points. And notice this time our equation f of x equals 1/2 of x. I should have said that in the beginning. That's what makes this a decay function, because that a value is less than 1. So here's some examples. We've got decay functions, which start on the top left with those fractions to an x exponent, and they go down. And our growth functions rise to the right. So 10 to the x, 3 to the x, and 2 to the x. Remember, the big difference between growth and decay functions when we look at the equation is our a value. If a value is greater than 1, then it's increasing. It's a growth function. If it's between 0 and 1, it's decreasing. It's a decay function. That would be something important to write in your notes. Now let's look at the graph of f of x equals 5 to the x. I know that this graph is going to be increasing because 5 is bigger than 1. My a value is greater than 1. On your graph, you can see that we have the point 0, 1 and the point 1 comma a, 1 comma 5 in this case. We also have the point -1 comma 1/5, but I didn't quite mark it on the graph just because it's hard to see. Our domain is -infinity to infinity because our arrows go forever in the left-right direction. And our range is from 0 to infinity. The lowest part of our graph is going to be at 0 on the y-axis, remember, because we have an asymptote. And then it's going to go up to infinity. Our next example, we are graphing f of x equals -2 to the x. So we're looking, the gray graph would be 2 to the x, and that negative is just going to reflect it down. So we get our blue graph, which is -2 to the x. Notice again that we have our 2 points going on here, but this time we have 0, -1, since we reflected down. And then we also have the point 1 comma a, or 1 comma -2. Our domain, -infinity to infinity, and our range this time is from -infinity up to 0, since we've been reflected. In example 3, part B, we're graphing f of x equals 2 to the x plus 3. Anytime we have a number added or on or subtracted off of x, that's going to be a left-right movement. So this is going to be left 3 since it's a plus 3. So what we did is we took the gray graph, y equals 2 to the x, and we moved all of our points left 3. So again, we see those points 0, 1, 1 comma a, and then moved those left 3. Part C, we're graphing 2 to the x minus 2 minus 1. The minus 2 is a right movement of 2, and the minus 1 on the outside here means down 1. So I'm taking those same 2 points, I moved them right 2 and down 1.